Hello everybody, welcome back to Fundamentals of Physical Geography and Step 7.1. In this unit we're going to be looking at systems, forces and connections, the whole idea of a systems approach to physical geography and the way in which that helps us to flag up the ways in which different components of our physical geography environment are all connected together. So as it says here on the introductory slide, at this stage you're ready, I hope, to put together the building blocks that we compiled in earlier sections, and we can see how energy, materials and processes, those big starting points that we engaged with right at the beginning of the module, we can see how those fit together into what we call systems. And the systems approach, the systems way of looking at things, is a really important thing for physical geographers to understand. We'll then go on and we'll consider some of those systems in more detail. So we'll look at landscapes, we'll look at the hydrological cycle, we'll look at biogeochemical cycles, different ways in which people have put together an understanding of the physical landscape using this systems terminology or these systems concepts. And the very notion of systems, the idea that we can organise information in this way, is itself an important idea within physical geography. So make sure you do some of the background reading on the nature of the systems approach. As always, there are set readings within the unit and also within the basic textbook that you're hopefully already familiar with. So let's launch into Unit 7.1 and think about systems, connections and forces within physical geography. So the first thing we should mention is the idea of systems. Now what I'm going to do throughout this section is I'm going to give you a little bit of an introduction now in this video, but then I'm going to refer you to separate videos in which I'll talk about some of the key themes at the whiteboard and illustrate them in a slightly more, hopefully a slightly more helpful way. But just to introduce the concepts first of all, let's think about the idea of systems in physical geography. And when thinking about systems, I particularly want to emphasise the idea of connectivity, because from our point of view, thinking about how physical geography works, it's connections within the systems, or points where connections don't exist within systems, that are really important in helping us to understand how those systems work. So I've just put on this slide a number of terms that you need to make sure you're familiar with by the time we've finished this unit, and that might come from the video mini lecture that I'm going to give you later in this unit, or from your independent reading. But make sure you understand first of all just what we mean by the idea of a system, and in particular make sure you understand the difference between open systems and closed systems, systems that have inputs and outputs from the system as a whole, and systems where everything is contained within the unit that we're concerned with. Make sure that you understand the notion of stores, of inputs to stores and of outputs from stores, and therefore the idea of flux or flow or transfers in and out, so through a storage point within a network. Make sure you understand the concept of equilibrium, where inputs and outputs are in balance, and therefore equally the concept of disequilibrium, where systems aren't in that kind of balance. And we'll talk about equilibrium concepts again later on in the module. Connectivity, like I said at the top, well, I'm going to mention it again at the bottom because it is such a unifying idea within the notion of the systems approach. Always think about the connections within our system, because that really is what makes a system, the connectivity or lack thereof within it. And then make sure you can give some specific examples, whether it's a mass balance of a glacier system, or the hydrological cycle, or biogeochemical cycles, or the Earth's energy balance as a system. We've already encountered systems in this module. You've seen me draw systems on the whiteboard before, and I'm going to do it again in just a minute with you. So you're kind of already familiar with the idea of a system, even if you haven't necessarily used this specific terminology to understand it. So have a look at the separate lecture video, do a little bit of reading, and make sure by the end of this week that you're happy with the idea of systems in physical geography. Now the second big theme, if you like, or the second idea that I want to bring back today, and I've touched on it previously in the module, I want to talk about shear stress. Now there are different types of stress or force that we're concerned with in physical processes, and a big distinction is between what we call normal stress and shear stress. And normal and shear simply refer to the direction or orientation of the stress relative to a surface that we're interested in. So for example, here gravity is working through the bench and exerting on my pen a normal stress, normal being at right angles to the surface. If I push the pen, then I'm applying a sideways force, a shear stress parallel to the surface. Normal stress is normal to the surface, shear stress is parallel to the surface. Now I don't know if you noticed that my pen rolled off the bench while I was talking, and that's because my bench isn't perfectly horizontal. It slopes a little bit down in this direction. And what happened while I was talking there is that gravity was pulling the pen down onto the bench, but because of that gradient, while some of the gravitational force was normal to my slightly sloping surface and holding the pen down on the ground, a small amount of the force was actually resolved, the gravitational force was actually resolved parallel to the surface as a shear stress, and that's what was dragging the pen sideways across the bench and off of the edge. So if you have a perfectly horizontal surface, gravity is going to be normal to that. If you have an increasingly sloping surface, then less and less of gravity is normal to that surface, and more of it is shear to it. So if I try to put my pen up against a vertical surface, well, it won't stay there because there's no normal stress holding it there. If I hold my pen against a surface, well, I'm now applying a normal stress with my hand, holding the pen against that surface. So normal stress perpendicular to a surface, shear stress parallel or across a surface. Now, lots of physical geography is about things moving downhill. In other words, where there's a slope, gravity can get the better of objects that are on that slope and make them move downhill. Whether it's on these slides, we've got some lava flowing down a hill slope. We've got a little mass movement on a hillside in Spain there, and we've got the edge of the Greenland ice sheet there. So you've got an ice sheet moving across a continental scale territory, and all of those forms of movement are driven by shear stress, sideways or lateral stress acting on the material. So it's energy on material driving movement, or driving a process, if you like. So we have this relationship between the stress driving a movement, the resistant or the strength or the friction resisting a movement, and if the stress is greater than the strength, then we get what we call strain or motion or movement in response to the applied force. And that relationship between stress, strength and strain is central to a lot of physical geography. So I just wanted to flag it up at this stage. I'm going to do a separate little video, mini video lecture for you, talking about it on the whiteboard later on in this unit. But just be aware that these driving forces are again another of the big connections that apply to all sorts of physical geography, whether you're studying coasts or glaciers or rivers or landslides. Stress, strength, strain relationships are central to all of them. So it's one of these big connecting points, if you like, across the whole of physical geography. Now, our module isn't particularly numerical, but when you're talking about shear stress, you will probably in your reading encounter a couple of equations, or a number of different equations, or so they appear, relating to how shear stress drives motion in different environments. A really important point that I want to make in this session is that even though you might think you're encountering lots of different equations talking about shear stress, you're typically actually only encountering versions of the same single equation. I often joke with my third year glacier students that there are really only two equations that you need in glaciology, and it kind of applies to a lot of physical geography. If you understand a couple of basic equations, then really you're seeing the key relationships in your area of the subject. And for shear stress, well, I've put an example on this slide. For glaciologists, for example, I do a lot of work on glaciers, so for me, my first thought when I think of shear stress are these two equations. Tau equals rho gh sine alpha. I've written it there as T equals rgh sine A. It really doesn't matter what symbol you use, but tau equals rho gh sine alpha. And that's the equation which determines, that tells you what the shear stress is, what the driving force behind motion in a glacier is going to be. And I'll draw this on the whiteboard for you in just a second, but what it's saying is that the shear stress is a function of rho, the density of ice, g, the force of gravity, and h, the thickness or the amount of ice. So rho, g and h basically add up to the weight of ice that you're looking at. And A is the surface gradient. Remember, we talked about this, the gradient of my surface here, determining how much shear stress as opposed to normal stress I had. And the steeper the slope, the more the shear stress and less the normal stress. The flatter the slope, the more the normal stress and the less the shear stress. So for a glacier sliding over a surface, it's all to do with gradient and weight. That gradient and weight give us our shear stress, our driving force. The second equation on the slide that you can see there, Glen's flow law, well again this is for glaciers, and Glen's flow law is the equation that tells us, well, given a certain amount of stress, how much movement, how much strain are you going to get? And the equation there, E equals A times tau to the n, what that is saying is that E is proportional to tau, so the strain, the movement, is proportional to the amount of stress. But there are a couple of other terms in there. The A term is just a multiplier. You can have it just a little bit multiplied by stress, or you can have it a lot multiplied by stress, depending on whether you make A small number or a big number. And A is simply a parameter for the hardness or the viscosity or the stiffness of the ice, and that's temperature dependent. So warm ice is more deformable than cold ice. Cold ice is harder than warm ice. So the strain is a function of how much stress you're applying multiplied by a number determined by the temperature and hardness of the ice. But then E equals A times tau to the power n, it's raised to a power, it's an exponent. In other words, if you increase tau just a little bit, you'll increase strain quite a lot. So those two basic equations, tau equals rho gh sine alpha, the shear stress equation, and E equals A times tau to the n, Glen's flow law, between them they give you the tools or the relationships that you need to calculate how ice is going to deform under its own weight in a glacier. And that's one of the main ways that glaciers move is by ice deformation in response to shear stress. Those two equations enable you to calculate how that's going to happen. That shear stress is also what drives basal sliding or deformation of a glacier substrate. So all the major forms of motion in glaciers are controlled by that simple equation, tau equals rho gh sine alpha. Now you might think, oh, what's the point of learning that for glaciers? I'm going to have to learn another one for mass movements and another one for lava and another one for rivers. Well, no, not really. And I've just put one example of that up on the slide here. If you go and look up mass movements in one of your textbooks and look up, well, what's the driving force behind mass movements, it'll say, the driving force, the driving stress, shear stress in mass movements. You're interested in tau, and you'll say, oh yes, I am. I'm familiar with tau from what I did with glaciers previously. But then it'll throw you by saying, well, tau equals W over A sine alpha. And you'll say, that's different from glaciers, because with glaciers it was rho gh sine alpha. But actually, W over A is actually just a different way of saying rho gh. Rho gh is the weight of the ice bearing down on the point where you're trying to calculate your shear stress. Well, in the shear stress equation commonly used for mass movements, the W is for weight, which is essentially rho gh. So you sometimes get confused, think, these equations are different. But just be aware that often different parts of the discipline use different terms to actually describe exactly the same thing. So the weight pressing down on an area for a glaciologist is rho gh over a point. For a mass movement scientist, well, they're interested in weight over an area, but they call it W over A. So tau equals weight over area times sine alpha for mass movement is just the same as tau equals rho gh sine alpha, weight over a point, for a glaciologist looking at sliding. So in different environments, the same relationship applies, and that's the really important point to take away from this. Even don't worry about the equations at this stage, just think, there are fairly straightforward equations that help you to identify what controls the driving stress and then allow you to calculate what the movement will be in response to that driving stress. And at first glance you might think they're different for different topic areas, but in fact they're pretty much the same for different topic areas. And I'm going to put up a separate video mini lecture just to say a little bit more about shear stress. So you can have a look at that if you want to look at this in more detail and get your head around it a little bit more clearly, perhaps. But I just want to finish this little bit on shear stress by showing you these couple of pictures. And the top picture there is a photograph of the summit ice cap of the volcano Cotopaxi in Ecuador, with a glacier coming down off that ice cap. And if you look at the shape of the upper portion of that glacier, it almost looks like a little bowl or an amphitheatre shape. And then look at the mass movement down below, which is orders of magnitude smaller. It's just a few meters across, whereas the glacier in the top picture is a kilometre or so across. Way, way smaller, a little mass movement in southern Spain on the hillside there. But the morphology, the shape of the feature, is very, very similar. And there's a diagram at the bottom from the USGS which illustrates the primary components of that type of landslide or mass movement. And you could almost redraw that diagram virtually unchanged for certain types of glacier, because the principle, the idea is the same whether you're dealing with a glacier or whether you're dealing with a mass movement, in that you have driving forces, shear stress, controlled primarily by gravity. You have materials with particular characteristics, the ice or the sediment on the surface there, which have a certain amount of resistance. If the driving force overcomes the resistance, we get movement, and then the mechanisms or processes of those movement lead to features on the ground surface or on the ice surface. And look, the features are actually very similar. And students sometimes say, well, how can we study the whole of physical geography? It's so broad, there's so much stuff. And I say, well, look at this example. A lot of the concepts that you need apply to many different situations across glaciers, coasts, landslides, waterfalls, whatever it might be. And this is a nice illustration of how, if you can get your head around the basics of energy, materials, processes, and if you can get your head around the basics of stress, resistance, strain, well, then that gives you a real head start into understanding lots of different process environments or lots of different physical geography settings. Anyway, if you want to know more about that, I'll put up a separate little lecture in the same block on the KLE for you to chase up shear stress in a little bit more detail. But I want to move on now in this introductory item just to say a little bit about the idea of complex effects. I've been saying so far that everything can be kind of reduced and everything is simple and the same things apply everywhere. But I also want to make the point that one of those simple ideas that applies everywhere is that life can be quite complicated in physical geography. You can make a single change somewhere, you can change one part of a system, and that has implications for other parts in the system because the different parts of the system are connected. And that's one of the ways that you can identify or define or characterize a system. It's made up of components, and if you change one of those components, or if you change the relationship between two of those components, that will have rattle-out effects that impact elsewhere in the system. So I can do something down here in my system, and because of that, changes will occur that affect something over here in my system. And I just want to give you a quick example of that. Again, I'll do a separate little video to illustrate it, talk through it on the whiteboard in case that works better for you. But I just want to say something about aspect. And aspect, that's a term that just means what direction is something pointing in. So if you have you can think of it even at a planetary scale with the sunny side and the shady side of the Earth. Well, this aspect is pointing in that direction towards the fluorescent light. This aspect is pointing in that direction towards the dark. The same is true of a valley. You have a sunny side and a shady side, or a mountain. You have a sunny side, a shady side. You have a side which is pointing towards the equator, a side which is pointing towards the pole, a side which is pointing into the prevailing wind, a side which is pointing away from the prevailing wind. That's what aspect means. And I just want to give you an illustration of how variation give you an illustration of how that idea of aspect can have a rattle-on effect through the system. So if you have different aspects on different slopes, it can make lots of other things change. So I'm going to talk through this as a whiteboard demonstration in just a second, but I'll just put the slide up here to remind you of that if you come back and look at this without necessarily going back and looking at the other video as well. But I'm just going to demonstrate on the whiteboard how differences in insulation on one side of a valley as opposed to the other side of a valley lead to variations in all sorts of other things: temperature, moisture availability, wind, the amount of snow cover, the duration of snow cover into the following year, when that water release, meltwater release from snow cover goes into the surface, and therefore how that affects moisture availability for vegetation at different times of year, how that affects soil development, how that affects overland flow, how that affects erosion, transport and deposition, and how that therefore eventually at the bottom of my list there affects the morphology or the shape of the valley, and can lead to an asymmetrical and uneven valley profile, steeper on one side and more gentle on the other. I'll talk through that separately in a separate mini lecture, but when you've had a look at that, maybe come back and have another look at this slide just to complete your notes. And look for some examples of your own. Here's just a random example that I pulled from my old pictures of southern Spain, where some of you might go on a field course in a future year. But this is a little valley in southern Spain, and you can see the two sides of the valley are different in their morphology. You can also see, conveniently on this photo, that one is on the sunny south-facing slope, the other is the less sunny north-facing slope. Now, in this case, it's clearly an area of land which is subject to human impact as well as to natural processes. And so this is a nice point to kind of draw towards a close in this little lecture, just to remind you that when we talk about physical geography systems, don't forget that there are human elements even in physical geography systems. That's one of the characteristics of geography, and one of the things we need always to be aware of when we're thinking about landscapes, that however much we're interested in the physical aspects of the landscape, in dealing with the Earth's surface, nowadays everything is affected by human activity. There's no part of the planet which isn't affected by human activity, even if we're just thinking in terms of the atmospheric composition. For example, composition of the atmosphere clearly influenced by human activity now. That has an impact on climate, that has an impact on surface processes, and so it rattles through the system. We have interfered so much with the physical geography system now that it is very difficult to separate out entirely physical from human geographies. And that's why geography is a single discipline, not two separate disciplines. But we'll come back to that perhaps in a later session. Here's another example, just to bring it back to the glacial example that we've been following through in some of these lectures. Here's a supraglacial stream, in other words meltwater flowing across the surface of a glacier. And again, you can see this is a very asymmetrical channel, and that's because the sunny side, the south, this was in Greenland, so the south facing, the equatorward facing side gets the sunshine, and that melts back. The stream cuts vertically, and then the sunshine erodes, melts back to create the sloping surface, whereas on the shady side, where the sun isn't doing that melting back, we retain a much steeper channel side. So it's just another little illustration, just to show that whatever part of the world you go to, whether you're in southern Spain looking at semi-arid hill slope, or if you're on the surface of the Greenland ice sheet looking at meltwater flowing over the ice, you can pull out these same ideas. And also in both of those examples as well, I'm seeing shear stress, I'm seeing normal stress, I'm seeing energy impacting on materials, I'm seeing processes varying from location to location. So you get the idea here, at this point in the module, one of the things that you should be doing, and this maybe will help you with your patchworks that you're worrying about at the moment, you should be seeing examples all over the place. In every picture you look at, every barking dog you see in the street should remind you of something to do with physical geography and these big themes and these connections that we're seeing between components. So just by way of conclusion then, you can read through these points for yourself. But I guess what I'm trying to deal with in this week's first unit is that the physical environment can be viewed as a complex system. That's our first key point. You can see the physical environment as a system. And you know when you're dealing with a system, because if you change one thing, well, it's connected to other things, so it changes those as well. So think of a system first of all as having these components that have inputs and outputs, and they're connected to other components, and we have fluxes and we have connections. That's what a system is. And that's a really important way of understanding connections within our physical geography environment. The second thing that I've tried to illustrate very quickly in this introduction is just that a few simple relationships and a few simple ideas: shear stress and normal stress, stress, resistance and strain, aspect as a controlling factor, and the complex relationships between things in systems. Those simple ideas that we can keep coming back to, whatever bit of physical geography we're looking at, they're really important for you to always have in your mind. That thinking geographically is always being aware of these kinds of relationships and these ideas of connectivity. So make sure you can explain and illustrate these things that we've been talking about, and ideas such as positive and negative feedback that you'll encounter in your literature, the idea of components, stores, fluxes, the idea of equilibrium that I'll mention in one of the accompanying mini lectures, and that we'll come back to in detail later in the module. But mainly, as you go away after doing this step, look for more examples. And I say this is a great opportunity for your patchwork assessment that you're doing. Look for examples of connectivity within systems, such as my example I just gave you of the valley asymmetry. But there are hundreds, there are thousands of other examples out there for you to go and find. So I hope that you'll do that. So having watched this video, go back onto the KLE or go back onto the SWAY where you found this video, and look for the accompanying mini lecture sessions where I'll talk about in a bit more detail some of those examples that we've covered, systems, stress and aspect that we've covered in this introduction. Okay, thanks very much.